And finally, we come to question 11, which is the theory type question on this sample final exam. What we have here are 3 proofs, one from each of the 3 major sections of the course. Now, it's very easy to get intimidated by theory type questions, but you can make it as easy on yourself as possible by really just boiling these questions down to their essential parts. What information are you given? What information are you asked to find? And then you can concentrate on figuring out, well, what's the connection between those 2 pieces of information? Sometimes, in general in mathematics, these connections can be quite difficult and obscure, but in a typical Math 2050 final exam, we're not going to make life that difficult for you. We want you to use the basic facts and ideas that we've presented in this course to help you draw those connections. So let's see. Part A tells us that we've got a plane pi, and it's spanned by 2 vectors e and f. We want to prove that if we've got another vector v, which is orthogonal to both e and f, then it must therefore also be orthogonal to every vector in the plane pi. Okay, a few things going on there, but let's break this down into all the pieces of information that we're being given. So first of all, we're told that pi is a plane spanned by these vectors e and f. What does that mean? What does it mean for 2 vectors to span a plane? It means that any vector in the plane is a linear combination of e and f. So, let's let u be any vector in pi. Then u is equal to a scalar k times e plus another scalar L times F for scalars K and L. And so U in this case now, this could be absolutely any vector. This is not one particular vector or even just a certain group of vectors. This represents every vector in the plane pi. The next thing we're told is that we're going to assume that we've got a vector v, which is orthogonal to both e and f. And so orthogonality means that the dot product of those vectors has to be 0. So v dot e has to be 0, and v dot f has to be 0. So we assume that v dot e is equal to 0, and that v dot f is 0. And so we want to show that v is therefore orthogonal to every vector in pi. But we just defined this vector u, which represents every vector in pi. So what we really want to do is we want to show that v and u have to be orthogonal, and therefore we want to show that v dot u is also equal to 0. Okay, so there's our given pieces of information. There's the thing that we need to obtain. How do we connect the two? Well, if we look at this expression v dot u, because we know how to write u in terms of the vectors e and f, we can take that dot product and we can write it in a more useful form. So v dot u is really the same thing as v dotted with k times e plus L times f. The dot product is distributive. If you watch the video for question 1, you'll have already reviewed that idea. So I can distribute the dot product. I can write this as v dot k times e plus v dot L times f. And again, as we discussed in the video for question 1, any scalars involved in that process can be factored to the front of the appropriate term. So I can further write this as k times v dot e plus L times v dot f. But we've made the assumption here that v dot e is 0, and we've assumed that v dot f is 0. So that's the scalar k times 0 plus the scalar L times 0, and it doesn't matter what scalars k and L might be, if we multiply them by 0, we get 0. Therefore, v dot u has to be 0, which shows that V and U have to be orthogonal, so V has to be orthogonal to any vector in the plane pi. That's all we need to do for part A. Let's move on then. Part B. Now we're getting into some matrix type stuff. And so we're told that we've got a matrix E such that E squared is equal to E. And we've got a matrix A, which is equal to I, the identity matrix, minus 2 times E. Given that information, we want to show that the inverse of A is A itself. Okay. So, two pieces of given information. E squared equals E, and A is I minus 2 times E. The thing we want to show is that A inverse is equal to A. And how do we show that one matrix is the inverse of another matrix? We show that their product is the identity matrix. So in other words, in this case, we want to show that if we take the matrix A, we multiply it by itself, we get I. So we want to show that A times A, or if you prefer, A squared, is equal to I. Okay, well, we know that A is defined to be I minus 2E. So I can replace A times A with I minus 2E times I minus 2E. I can distribute that. I can write that as I times I, or I squared, minus 2 times E times I, minus I times 2E, plus 2E times 2E. And much like the dot product that we just talked about, matrix multiplication does allow us to pull scalars to the front of the appropriate term. So I can write that as I squared minus 2 times E times I, minus 2 times I times E, plus 4 times E squared. Now, matrix multiplication isn't commutative. I can't in general take the product of two matrices, call them M and N, and say that M times N is equal to N times M. That's generally not true. But in this case, almost all of the expressions that I've got here involve multiplication by the identity matrix. And what does the identity matrix do to matrix multiplication? Well, it says that whenever you take the identity matrix and multiply it by anything else, you're just left with that other matrix. So for example, I squared, or I times I, the identity matrix times the identity matrix is just the identity matrix. So that's just I. Minus 2 times E times I is just minus 2E. Likewise, minus 2 times I times E is just minus 2E. And then we've got our plus 4E squared. So I can simplify this and write it as I minus 4E plus 4E squared. But here's where our other given piece of information comes in. We're told that E squared equals E. So I can write this as I minus 4E plus 4E. And so minus 4E plus 4E, of course, they cancel each other out. So what am I left with? I'm left with the identity matrix. A times A is equal to I. So A inverse is equal to A. There's part B. Finally then, part C. Here we're told that A is a square matrix, and lambda is its eigenvalue, or maybe one of its eigenvalues. We want to prove that if A squared is equal to I, then either that eigenvalue lambda is 1, or it might be negative 1. Okay, so again, two pieces of information. We're told that A is a square matrix, which it has to be if we're going to be talking about its eigenvalues, or for that matter, invertibility. So A is a square matrix, but specifically, it's a square matrix with eigenvalue lambda. So what does that mean? Well, it means that if x is an eigenvector, then A times x must be equal to lambda times x. Okay. We're also told that A squared has to equal the identity matrix. How are we going to bring those two things together? Well, the only way to make use of both of those facts is to take this relationship that A squared is equal to I and multiply both sides by the appropriate eigenvector x. So if A squared is equal to I, we have that A squared times x must be equal to I times x. On the right-hand side, we can use a similar idea to the one we just talked about for part B. The identity matrix times anything is just the anything. So I times x is just x. On the left-hand side, we've got A squared times x. But A squared is A times A. So I can think of that as A times x must equal x. And A times x, we just said, is lambda times x. So now I've got that A times lambda times x must equal x. Lambda is an eigenvalue. It's just some scalar. I can factor it out to the front. So that means that lambda times A times x has to equal x. And now I can do the exact same thing again. A times x is lambda times x. So that tells me that lambda times x must equal x, which I can simplify to write as lambda squared times x must equal x. Now, because the vector x pops up on both sides, the coefficient of x has to be equal in both cases as well. So if lambda squared times x equals x, that really means that lambda squared times x is equal to 1 times x. Thus, lambda squared is equal to 1. And so lambda is plus or minus 1. That's what we wanted to prove. That's question 11. That's the Math 2050 sample final exam. I hope you found this useful. Good luck with your Math 2050 exam and all your future coursework.